My name is Meg Farinsky, and I am a math and physics double major at Central Connecticut State University. I'm here at Cornell this summer for the 2024 CLASSE REU. My project for these 10 weeks was designing a high-pressure rinse mount for superconducting material samples with my lovely mentors Nicole, Jake, and Adam. I spent the first 2 weeks of the program learning about superconducting radio frequency cavities, and from there spent much of my time using Autodesk Inventor to design the HPR mount that would be used to clean samples for the Cornell high-pulsed power sample host cavity. Over the weeks, I learned a lot about Inventor and about the design process as this mount went through numerous iterations. The final design is in 3 parts: the back half plate, which leaves space for the new splitter arms on the HPR, the top plate with 4 mounting options allowing for use of the existing central HPR wand or simultaneous multi-sample cleaning, and the sample holder itself, designed to optimize drainage away from the sample. The sample, internally known as the chip, is held in place by a clevis pin, the chip clip, if you will. This mount will be fabricated from a plastic called Delrin, which is resistant to water absorption and, by extension, very dimensionally stable. While each iteration of this mount was pending review, or as the final design awaited fabrication, I got to spend time in the lab. My first task was to clean hardware using the small ultrasonic in Newman Labs Class 100 cleanroom. While the ultrasonic is fully automated, all surfaces coming into contact with the hardware must first be cleaned with methanol or isopropyl alcohol. Any particulates in the system would cause a premature quench. Once Nicole had assembled her cavity, I helped her leak check using this Lenovo S10-2 laptop that will be legally eligible for its driver's license this October. The assembly was transferred into the pit, waveguides attached, and the whole thing was bolted into place. Nicole pumped the pit down to vacuum, and then we filled the liquid nitrogen layer, and then we filled the liquid helium layer. The pit is covered for testing with this massive 90-ton radiation shielding block of high-density concrete. With this in place, it's safe to power up the Klystron, a 1 megawatt relic from Reagan's Star Wars project. To put that into perspective, 1 megawatt is enough to power about 670 homes. At this point, everything is set for testing. The computer hooks up to a plethora of analog devices monitoring waveform output from the Klystron. This data is used to find magnetic quenches, hopefully experimentally confirming the quench field of niobium-3 tin. This work is supported by the U.S. National Science Foundation REU Award for Accelerator Physics and Synchrotron Radiation Science.